Hey everybody, this is your video for January 7th, 2020. The first thing we'll be talking about is topic 10 in Unit 3, which is solubility. Go ahead and pause the video now and take a minute to write down this learning target in your own words. So the first thing we'll talk about are the factors that affect solubility, such as structure, temperature, and pressure. We'll talk more about temperature at the end of this video, and I will show you some solubility curves. What we're mostly going to focus on right now is the structure. When we talk about like dissolves like, and I want you to think about this. When we talk a lot in chemistry, we think about generalities, and that is what we're going to think about now. Most of the time, and there are of course exceptions to every rule, but most of the time, polar molecules are going to dissolve other polar molecules. Nonpolar molecules are going to dissolve other nonpolar molecules. Okay. They usually are going to be miscible. When we have polar molecules, they're going to be miscible with other polar molecules, and nonpolar molecules are going to be miscible with other nonpolar molecules, which means they're going to be soluble in all proportions. Right. All right, here we have water here. Here's a water molecule. And in the middle here, we have our methanol molecule. On these molecules, the oxygens on both of these have two lone pairs on all of these here. So what you see here with a polar water molecule and a polar methanol molecule, what happens is of course, we know that the oxygens in the waters acquire a negative charge, and that same thing actually happens with the methanol. And then our hydrogens here acquire a positive charge. Okay, and so what happens is the positive poles on the methanol, they're going to line up with the negative poles on the water, and then the negative poles with the methanol molecules are going to line up with the positive poles on the water. And that attraction is going to hold that methanol in solution. So again, we're not going to talk about here, we're not talking about an ionic like a sodium chloride dissolving and breaking up in ions. So this methanol here is not going to break up into a bunch of oxygen ions and hydrogen ions. That's not what's happening here. We are seeing that there are two liquids and it's holding it in solution, so they're not separating. It's not going to be an oil water. These are mixing equally together. Okay, so next what you see here is we have two nonpolar molecules here. So this is going to be C6H14 hexane and octane, which is C8H18. These are miscible. They form strong London dispersion, forces of attraction with one another. Again, remember miscible means they're soluble in all proportions. So these are going to hold one another in solution just because of those strong London dispersion forces. Remember, London dispersion means that they're going to have those temporary dipoles rather than the dipoles, like a dipole-dipole. These are not going to be the same. Okay, so when we have ionic compounds, an ionic compound is not going to have any intermolecular forces, but they are going to be very polar, because that means we're going to have a positive pole and a negative pole. Okay, when we have that positive and negative pole, that means that they are going to be attracted to the water. So when I show you this here, okay, so you have this positive in the sodium here. This positive in the sodium is going to be very attracted to the negative in the oxygen. And the negative here in the chlorine is going to be very attracted to the positives in the water. In the hydrogen. So what happens here is they're going to actually break them, because the force of attraction between this negative chlorine and this positive in the hydrogen, it's actually stronger than the force between the sodium and the chlorine. So it's actually going to break them apart into aqueous ions. When that happens, the water molecules literally attach themselves to the ions, and they actually drag a number of the ions of the water molecules around with them as they travel through the solution. So that is why they actually break into ions and dissolve. So this is a little bit different when we're talking about liquid-liquid polar and polar, the ionic compounds are just a touch different than the two polar molecules dissolving in one another. Okay, one other thing I do need to point out, smaller ions do actually have a stronger electric field. That is because of the electrons. They are actually going to drag more water molecules around with them because they have a greater effective nuclear charge. More water molecules are going to attach to it. So this lithium down here, because it has a greater effective nuclear charge, it's actually going to drag around more water molecules with it. Alright, so I paused the video. I'm not sure where, so I'm going to go over this. If I went over it already, I apologize for that, but I do want to tell you that some ionic compounds do not dissolve in water. The solubility of ionic compounds is explained right here through Coulomb's law. So some ionic compounds, if the cation-anion attractions are stronger than the ion-dipole attraction, then the compound is not going to be soluble. So where we were earlier when we were looking at our sodium and our chlorine right here, our sodium and our chlorine were more attracted here. If we look at this, our sodium and our chlorine were more attracted to, like our chlorine here is going to be more attracted to our positive hydrogens, and our sodium is more attracted to our negative oxygens than the sodium is attracted to the chlorine. So our anion cation, the sodium and the chlorine, are less attracted to each other than our ion dipole, which is our hydrogen chlorine or our oxygen sodium. So the ion dipole is stronger than the cation anion attractions here. So because that is the case, that is why this sodium chlorine here is soluble in water. However, that is not the case with every single ionic compound. Okay, also to point out, if you look down here, this is important, you may want to make a note of this, ionic compounds are not going to dissolve in nonpolar solvents because nonpolar solvents do not carry permanent dipoles. That is also important to remember. So as a general rule, magnesium hydroxide is not soluble in water, but barium hydroxide is soluble in water. If we were to draw magnesium hydroxide, we would have an OH here, a hydroxyl group, and let's just say our magnesium is in the middle, okay, and our hydroxyl group is here. This bond here between the magnesium and the oxygen is going to be very short because magnesium is rather small. Whereas if we have barium and hydroxide, if we have our hydroxyl groups here, our barium hydroxide is going to be a longer one. Okay, so that longer bond is going to be easier to break. It's not as strong. This is going to be much stronger than this bond down here. This is going to be a weaker bond than the magnesium hydroxide. Okay, so because of that, this barium is going to be soluble in water. The barium hydroxide will be soluble in water, whereas the magnesium hydroxide will not be soluble in water. Okay, and the general rule of thumb here is, let me show you. Okay, the ion dipole form of attraction, and here's your little diagram. Okay, the ion dipole forces of attraction between magnesium and water are stronger than the ones between barium and hydroxide because of that distance, and we've discussed that before. Okay, these two forces work against one another through Coulomb's law. Okay, and we look at that, the lattice energy accounts for the cation anion attraction, and hydration energy accounts for the ion dipole attractions that are going to try to pull away the ions from one another. Okay, now for alkaline earth metals, and I will show you a periodic table here real quick. Okay, so here's our periodic table. So our alkaline earth metals are that second group there. So here's our alkaline earth metals right here. And so these alkaline earth metals are going to, these alkaline earth metals, when they bond with the hydroxide, the lattice energy decreases more rapidly than the hydration energy when you move down the group. So as you move down this group here, the alkaline earth metal hydroxides, the lattice energy is going to decrease as you go down, meaning that the energy between the barium and the hydroxide is going to decrease, and the ion dipole energy will increase very rapidly. Therefore, as you go down the group, they are going to be more soluble in water. Okay, so the last thing that the last thing I want to discuss here is solubility and temperature. We discussed this at the very beginning of this video, and I want to just go back and give you a quick solubility curve tutorial, you could say. The first thing we want to discuss here is the solubility of potassium sulfate, potassium nitrate, and sodium chloride. You'll notice with those curves they increase as in temperature increases, meaning that the higher the temperature, the more of that substance that can be dissolved in water. So for example, we'll look at potassium nitrate since that curve is the most dramatic. At 10 degrees, I can dissolve, it looks like about 12 grams of solute, which means potassium nitrate, per 100 grams of water. If I move up to maybe 50 degrees, I can dissolve about 50 grams. 80 degrees, I can dissolve about 95 grams, and so on. So it increases as temperature increases. I can put more and more potassium nitrate in. Okay, this means that these three, because that curve increases, those three are endothermic reactions. When they dissolve in water, they're going to be endothermic. Now, if we look at cesium sulfate down there at the bottom, if I look at cesium sulfate at the bottom, okay, cesium sulfate, for example, is going to be exothermic. Okay, as cesium sulfate, it decreases with temperature. So the higher the temperature, the less cesium sulfate can be dissolved in water. And this isn't extremely dramatic, but if we look at 0 degrees Celsius, I can dissolve maybe 40 grams, but then if I move on to 30 degrees Celsius, I can only dissolve 30 grams. And at 40 degrees Celsius and 50 degrees Celsius, it gets lower and lower and lower. Okay, this is an exothermic process. Okay, this is generally the general rule. Most solids are going to increase their solubility as the temperature increases, but there are a few, like cesium sulfate, that do decrease. Even though this is not something that happens all that often, you would have to have a solubility curve or some kind of data to figure that out. And lastly, we are going to talk about gas solubility and temperature. Gases, of course, we know have very weak intermolecular forces, which is why they are gases at room temperature. Okay, like for example, nitrogen and oxygen, they form very weak dipole-induced dipole forces and weak dispersion forces with water. As kinetic energy of particles within a solution increases, which we know that happens when temperature increases, aqueous particles break free from those weak attractions and they re-enter the gas phase. So, for example, when you're heating a pot of water, you're going to see bubbles forming. And when those bubbles are forming, that actually happens way before boiling point. That is because the gases like oxygen, nitrogen, and carbon dioxide that are in our atmosphere, they're leaving their aqueous state and they're re-entering the gas phase. And that happens because they form weak dipole-induced dipole forces. And as that kinetic energy of the particles, or as they heat up within a solution, they are breaking free from those weak attractions and they're re-entering the gas phase. Okay, so this is the end of this video. We are about to go ahead into the classroom and get some partner work and independent work done. I hope this helps.